be kind of listening. All right. So we've already talked about manipulation of data. And we talked about it in terms of the polygraph test, the results. And we looked at two that were showing the same result, but it kind of looked like one person was lying and one was not. And all it was is that they were using a different scale on one graph than on the other one. So you have to kind of watch out for things like that and pay attention to how they're showing you the data because it can easily be manipulated. So I kind of mentioned back then that one of my favorite things is to watch some of these commercials and hear how they're talking about their drug. So pretend there's a brand new drug called the Liberator. So LB pounds, get it? This Johnson's so funny. Anyway, brand new weight loss drug, right? Participants in our study who took the Liberator, they lost 4 times more weight. 4 times more weight. I want to lose 4 times more weight, right? Than some other little schmo that's, not losing 4 times more weight. I mean, that sounds really impressive, right? 4 times more weight. Well, set up a lab experiment. You give one group a placebo. Does that word sound familiar? Have you heard placebo before? It's like sugar pill. It looks exactly like the real drug. It just doesn't have any of the medication in it. So one group gets a placebo. The other group gets the Liberator weight loss drug. So the group that was given the placebo, their average weight loss is 1/4 of a pound. That's over all the people in the group, 1/4 of a pound. 4 times more than that is a pound. 4 times more is still basically nothing. I mean, it's just a pound. But if I were the person that owned that company and was trying to sell that drug, you better believe that I'm not going to put that part of the information in there. I'm going to talk, it is 4 times, I'm not lying at all. That is absolutely accurate. Just leaving out the detail that the, weight loss was 1/4 of a pound. So you got to kind of watch out for that. This was an actual graph, Rhode Island, not us, an actual graph by their health department that was put out. What does it look like as far as males versus females contracting COVID-19? It looks like guys get it a whole lot more than females. But if I take that same graph and I just simply get a more reasonable, counting pattern, I mean, there's only a difference of not even 10, I don't think. So 78, yeah, it's not even 10. It's 87. So what is that, 9? I can't math in my head, but it's less than 10, right? So now if I use a more reasonable scale, it doesn't look as as extreme as this one does. But, it depends on what your point of view is. Or it depends on, whoever the politician is. They're just given this by somebody. And so the politician goes out there and says, guys, stay home. Don't go out. All right, girls, you can go out. When in reality, it's basically, pretty much the same risk for whether you're male or female. The problem is that things like this then, you get laughed out of office or you lose your credibility. So nobody's going to believe anything that you say after that. When it was, just reading a graph, you just don't have the data displayed in a reasonable way. Why do we even bother with data analysis? So that kind of takes us back to the flip a coin, is 49-51, is that close enough to 50-50 sort of situation? Chances are up till now in your science class, if it was 51, oh, that's more than 50, so that did have an effect. Well, that's not necessarily the case. We have to take the data that we get from experiments and apply analysis to them to see if there's something really going on. So appropriate techniques, we have confidence in what we're telling people. So more data gives us confidence in what we're talking about, and appropriately analyzed data gives us confidence, and it leads other people to have confidence in us and what we say. Boop, oops, back it. Hey, easy there, going twitchy. Allows you to make claims with confidence. So the things that you say is backed with good data. You're not just pulling stuff out of the air. The big one is this an effect from my treatment? Or is what I'm seeing, is it just due to chance? Because a lot of times it's due to chance or due to a variable that you have no control over. Well, I didn't even know that was a variable. I didn't even know that would have an effect. And you didn't realize that it was affecting your experiment. All right, so standard deviation. I don't think that, I know that I will never ask you to make a standard deviation graph. I don't think that you will ever have to make a standard deviation graph on an AP biology test. I do think that you would have to be familiar with standard deviation and maybe have to analyze it or draw a conclusion from it. So standard deviation, this is the standard deviation graph, and it bell curve. Does the word bell curve sound familiar? Maybe. Bell curve is kind of like C's are the most, and then B's and A's, D's and F's. It's kind of, there's kind of an even distribution amongst everything. Well, we can apply that to especially like populations in science as well, but also to data. So mean is average, and mean is the middle line. If I can get that right there. Mean is the middle line on the curve. It's right on the top of the bell curve. So standard deviation is look like how does the rest of the data deviate from the mean? So the first, if this is the mean right here, this first section above and the first section below, that's kind of all grouped together. It's essentially the same as the mean. But essentially, that's all. That's like saying you flip a coin, you're going to get 50-50 heads, 50-50 tails. If it's 49-51, that's the same as 50-50. 48-52, that's the same as 50-50. That's what that same of others. That's what that's talking about there. Then this is one standard deviation of the mean. This is two standard deviations of the mean. This next section is two standard deviations. And then this one, it's probably more than the others, probably less than the others, but not for sure, So when we look at standard deviation, we're going to look at two below and two above, and we're going to kind of group all of that in together. That's going to be the data that we look at. These that are definitely less than the mean, definitely more than the mean, we're going to ignore that and say that those are outliers, and that's not part of the data that we analyze. So this is the data that we look at. That's two standard deviation above, two standard deviation below. And that, if you add all those together, that equals 96%, 95%? 95% should be. Like I said, I can't math right now. 95% should be. So whenever we use standard deviation, we're using data that we are 95% sure that our data is going to fall within that range. So not all of the bell curves look the same. The one on the left is much more compact. The one on the right is much more spread out. On the left, the mean is still that line in the middle, the black line in the middle. So that's your average. But now all the data that lies outside of the average is really close to it. So it's not that far away from what the average is. On the right, the mean is the middle line. But now the rest of the data is spread out pretty far from the mean. Take the worksheet that I gave you and flip it over to the other side. The top two graphs, you'll notice, kind of look like what I have up here. Oh, let me get the one that's not, that I haven't scribbled all over. All right, that's better. All right, so when we look at those top two graphs, and I have, since I want to kind of talk about that, I've labeled this one graph A and this one graph B. I think the mass numbers at the bottom, they're kind of hard to read, so I just kind of made them up. 1, 2, 3, 4. Oops, I did that wrong. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Just so that I can kind of talk about that and I have actual numbers to talk about. It looks like graph A and graph B don't have the same amount of data that's collected. It looks like graph B, they've collected a whole lot more data. Is that an accurate statement, that I have more data collected in graph B? sure what else is giving me a clue that there's not more data collected on B necessarily than on A? So their counting pattern, the scale that they're using, is different on those graphs. So we're just going to go ahead and say that they've both collected the same amount of data. And that's one of the things that you have to watch out for. But so if it's the same amount of data, then that kind of accentuates the fact that in graph A, it is so much more condensed into a smaller range, and in graph B, it's spread out a little bit more. All right, so I added a little bit of information, and leave yourself some room because we're going to sketch a standard error graph here in just a minute. But at first, it looks like graph B has more data. Look at the y-axis. And you can probably write it a lot smaller than what I had on there. But at first, it looks like graph B has a whole lot more data, but look at the y-axis. Their scales are different on each one of those graphs. So this graph might have a standard deviation of 5. This graph, because the data is spread out more, it might have a standard deviation, let's just say 10. And I'm making up numbers. But just to give you an idea, the standard deviation is greater than it is here. We'll come back to that here in a minute. But then I've labeled these other two graphs. So this is my graph C and graph D. Notice that the curve looks identical on both of these graphs. The curve looks the same. It looks like graph C has less data than graph D. Is that accurate this time? How do we know? Fewer bars, but then I go and look at the y-axis and I notice that the scales once again are different and this scale is higher than that scale, so I have more data on this graph. More data is good. The more data that you have, the better it is. More data means a more reliable, I think that's how you spell it, mean. More data means I have a more reliable mean. So that's always good. Mean like average, M-E-A-N. Mean, median, mode, mean. Sure, there's some math and science, and so this graph probably looks a lot like the histogram that we talked about yesterday or the day before or last week, because the bars are touching each other and it's continuous. Well, this would be like a population study. So we're looking at the mass of fish in a trout population at Robbers Cave, whatever, blah, blah, blah. And so there are some, here's the average. But there's some that are above, some that are below. This is how it's distributed. Okay? All right, so done with that for just a minute. Let's go back to this. Blop. All right. Standard error graph with standard error bars. I guarantee that you will be asked to make and analyze graphs that have standard error bars on there and that show standard error. So the first part of this graph is probably what you've seen before. It's the bar graph part. So the little gray bars that are on here, you're familiar with that, the XY axis. I mean, all of that's great. The new part is the little I-beams that you see on here. And these I-beams represent standard error. And standard error is how confident are you that, another random choice is going to be the mean or the average. So the first bar represents apples. And this is the price per pound of apples. So it says in US dollars. Let's just say, it says 12 major cities, okay? So you go in Oklahoma and you pick 12 major cities in Oklahoma, and you try and you find out how much a pound of apples is in each one. What I need you ladies to do today is set up, I don't know how many sets I have, set up as many as I have. And then we had some wonky results last year, so maybe you take 2 random ones and you take 2 random ones, unless there's only 4, then do them all. And test them and then tell me what blood type you get for your individuals. That will tell me if I have to wipe all that out or if it's still okay. I don't know if the stuff was too out of date. So, like, what do you mean? So, blood typing, serum A, serum B, A, B, RH. So a drop in each, 1 drop in each, mix it up, see what. Okay. So that's the lab paper. Yeah, let's get the needle nose, those in that little box right there. That should work. That way you can keep it a small amount. Okay. So according to the graph, apples averages about $2.25 a pound. From those 12 cities, they bought a pound in each of the 12 cities, took the price, averaged it $2.25. Same thing for plums. 12 cities, they averaged it, looks like about $1.50 a pound. Oranges, 12 cities, a pound from each, looks like about $2.50, $2.75 a pound. So that's the average. But for us, that's like saying 50-50. In real life, it's not always flip a coin 50-50. So what we're trying to find out is how likely is it that I go to another city in Oklahoma and a pound of apples is going to be $2.25. So we look up standard of error. And I'll show you how to calculate that later. This standard error bars right here, this represents 2 standard error, plus or minus 2. So here's my mean, here's my average. This is 1, 2 standard error plus, so plus 2. This is 1, 2, minus 2. So whenever you get your value for standard error, you add it to the mean twice to get the top bar. You subtract it from the mean twice to get the bottom bar. Same thing we did for plums, same thing for oranges. So great, now we've got these cute little eyes on here. Well, what does that mean? We can use that to analyze and decide how likely, how confident we are with that mean. For apples, I'm pretty confident because that little I-beam is relatively short and squat. It goes anywhere from 175 to 250. I'm pretty confident that if I go to another random city, a pound of apples is going to be pretty close to $2.25 a pound. Oranges, on the other hand, that standard error, anywhere from 175 all the way up to, it looks like maybe 350, 375. I mean, that's a huge range. I do not have a whole lot of confidence that I'm going to go and buy another pound of oranges and it's going to be about 250. I don't have a lot of confidence for that. Plums, but Mrs. Johnson, this I-beam looks the same as that I-beam, and yes, it does. The only problem is that the plums I-beam takes up almost the whole bar for plums. So this is saying that this should be an average about 50 cents, but it could be anywhere from 25 to 1. I mean, that's a huge range for that item. So I don't have a lot of confidence for plums either. For us, we're going to look at it more in terms of you have an experiment, here's your data. what does the data say? So we're not going to be looking at apples and oranges. I just kind of want to give you an idea of what those standard error bars are talking about. We're going to look at it, and you're probably usually going to compare at least 2 sets of data. So on the left-hand side, it's control and treated. So control, remember, our control group doesn't get the independent variable. Treated is getting the independent variable. We're treating it with our whatever the independent variable is. So for the one on the left, they both have relatively squat I-beams, but the big thing here is they really don't overlap. So the control has a bigger average than the treated. Then when I analyze my data and put my standard error on here, they don't overlap. That's telling me that there probably is something going on there, that my treatment is probably having an effect. On the one on the right-hand side, I've got 2 blue bars over here. This one looks like it's got a higher average than that one, but then when I do standard error to analyze it, those bars overlap. That's telling me that my treatment probably isn't having an effect. The difference in the average, the reason why this one's bigger than that one is probably just due to chance. That's probably it. So over here, since this one looks like my treated is having an effect, and this is enzyme activity, so my independent variable, it is making enzyme activity decrease, most likely. Oh, I thought somebody had a question. So flip over your paper back over. And so we're just going to sketch a couple of graphs based on the data in the, sketch a couple of standard error graphs based on the data in these graphs. Whoopsies. So for graph A, what is the mean mass? In graph A, what's the mean mass? How many kilograms? So my bar represents the mean. This is graph A. Graph B, what's the mean? That tells me nothing. The way it looks right now is that it's the same in both populations, which when we graph out the data in standard deviation, obviously that's not the case. Here, I can be pretty confident that if I take another random fish, it's going to be pretty close to that mean because all of that data is pretty compact. Here, I don't have a lot of confidence that I'm going to grab another fish and have it be close to the mean because the data is so spread out. Do you see how I can draw it that way? Does that make sense where I'm getting that from? And then normally I wouldn't put the letters on the bars. I probably shouldn't have put it underneath here, but just feeling. All right, so let's do the same for C and D. So sketch again. What's the mean for C? Are they different numbers underneath there than on the top? Oh, well, and that's, I'm going to go ahead and do it the same as the top, just simply because I can't see it, so I'm going to, I mean, I'm pretty sure that what we have here are the same graphs. Okay, and for D, what's the mean? Once again, that doesn't tell me anything. But more data means I have a more reliable mean. So even though they're about the same spread, I'm still more confident with D. That's probably not like A up there would have probably been something like that. So D is a little bit more, you know, there's still more error, chance for error. But C, I don't have enough data to really get a good idea whether or not That's a really good mean for that population. More data means it's more reliable. All right, how about that? Do you see where those bars come from? Where I got those lines? Why I drew the I-beams the way I drew them? More reliable means less standard of error. Less standard of error means I'm more confident that I'm going to pull another fish out and it's going to be 5 kilograms. Bigger, longer standard of error bar, more spread out data on this one. So I'm not confident that I'm going to grab another one and it's going to be close to the mean. On this one, I'm more confident that I'm going to be closer to the average because all of the data is compact. So there's not a whole lot of outliers. This one I'm not as confident about because it's already so spread out. Right? Let's see. Okay, we did that. Oh, yep, so we're on to this page. Go grab a couple of little Post-it notes. Grab a couple of little Post-its. So I'm looking at the front page, and I'm looking at these 3 graphs down here. The rest of the information is great resource. We're going to manipulate this. We're going to adjust it just a little bit. So in order for these blue bars to make sense, I kind of sketched to make a graph. So these are 2 types of fertilizer, and once again, I wouldn't normally write on the bars. The A and B would underneath, and then fertilizer would be my label. Height, notice I have metric units in parentheses, so I know what we're talking about. All right, days in science past, you would have just had the blue bars there. If you ignore everything else besides the blue bars, it looks like fertilizer brand A makes them grow more, right? Do you see how I can say that? Well, that's not a good conclusion. So now we take the data and we run statistical analysis on it. We do standard of error, and we add the little I-beams. The I-beams are overlapping. Because they're overlapping and there's a substantial amount of overlap, that tells me that even though A is a higher mean, a higher average, the plant's average taller than fertilizer brand B, that doesn't have anything to do with the treatment itself. It's just due to chance. There might be some other variable, or they're close enough. They're 4753. It's close enough to still being the same. So my conclusion would be along the lines of, even though fertilizer brand A averaged taller plants, the difference is not statistically significant. That difference is probably just due to chance. Or due to a variable that we didn't control, that we didn't realize was going to have an effect. statistically significant is the key. The analysis tells us that it's not any big deal, that it's not anything to write home about. On the middle graph, you'll notice that I think there's even a bigger difference in the bars. So the bar on the left for fertilizer brand A, it shows an even higher growth, even higher mean for the plant height, but there's still overlap. Now there's less overlap, but there's still overlap. So this is showing that there probably still isn't anything to do with my treatment. It's probably still something to do with chance. Then on the one on the right, now I remove everything else besides the bars. I'm saying, hey, for sure this one's bigger. But when we do statistical analysis on that, that helps to back us up and say that, yes, now there's probably something to do with our treatment. No overlap in those standard error bars. There's probably an effect. But once again, we're still not, this absolutely, fertilizer brand A is absolutely the best. That's like saying 4 times more, blah, 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 blah. It's still just probably. So hypothesis, supported or rejected, we don't use supported anymore. We say failed to be rejected because everything constantly needs more analysis. So even with these guys, the fertilizer brand A most likely had an effect. Still need to analyze it some more. You always need, I mean, for a supported hypothesis, you're always analyzing it, always. Because all it takes is one little change, one little variable, and it can totally destroy what you think's going on. All right, so just another example that's on there I kind of threw up there. I mean, this doesn't apply to us as much, but you know, we're usually comparing lab results. But let's say we run an experiment and we want to decide which subject students do the best in, are the most successful in. And so these are all test scores. So if I just compare math and biology, math, average, students average less than their test grade in biology. But in math, their standard error beam is more compact. So even though their overall average is less, they're probably all about on the same spot with the things that they had difficulty with. Biology, the average is more, but you might have had a couple people that were outliers and bumped that average up. Standard error beam is much longer, so that's showing us that those students, there's probably like something different that everybody had trouble with. They're not all on the same page. So another example, you can kind of look at that if you ever go back to that. I just wanted to show you the fact that there could be a graph that they plot points and put standard error bars on. I'm not ever going to have you do that. I hardly ever see that. However, be aware that that's what you're looking at here. That's showing standard error on each one of those points that are plotted there. Kind of squirrely if you ask me. Okay, so this is important worksheet. I would recommend that you put it in your AP Bio Lab notebook. So we had the first three sheets were the little scientific method, and then the next sheet was our notes over hypotheses. I would suggest you put it on the left-hand side, you know, the opposite side where the notes on hypotheses were at, because we're going to set up our next AP Bio Lab and then it will deal with standard error and standard deviation. So I would suggest that you turn it sideways. You want to see both sides. So 2 pieces of tape on the top, 2 pieces of tape on top on the other side.